So what I'm going to do is first I'll recall the notion of regular sequences and their analysis. And then I'll focus on two more specific questions, one relating to summatory functions and, surprise, surprise, the other one concerning divide and conquer recurrences. But let me first not simply assume, okay, you heard my talk last year, so you know what regular sequences are. So let's skip the introduction and go straight to the questions of this year. I'm not very happy with this approach, so please accept my apologies if you already know everything I'm going to tell in the next, I think, 7 slides or something like that. Okay, I'm going to focus on 2 particular examples, and I'll speak about these 2 examples first. So my example number 1 is find minimum and maximum via divide and conquer. So what are we going to do? We have a list of numbers, say we'd like to find minimum and maximum. We partition that into 2 sets of almost equal size. We look for minima and maxima in both sets. Then we compare the minima and we compare the maxima in order to find the global minimum and the global maximum. So that's a divide and conquer approach for finding minima and maxima. And I'd like to analyze the number of comparisons I might need. That's called M of n. And what's the number of comparisons in that example? Well, we take the larger half, n over 2 ceiling, the smaller half, n over 2 floor, compute to the thing recursively, and then we need the 2 additional comparisons to compare the minima and to compare the maxima. Good. As simple as that. And we can rewrite that if we are not very happy with ceilings and floors in the following way. So if n is even, then there is no smaller and larger half, but that's 2 times m of n plus the 2. And if it's odd, well, then we have m of n and m of n plus 1 plus 2. So a typical divide and conquer approach, just as one example of many examples you could do in that direction. Okay, that was example number 1. Example number 2, binary sum of digits. So binary sum of digits, well, I don't think I need to explain what it is. And we have a similar recurrence. So S of n is S of n halves plus Iversonian of the least significant digits. So if it's odd, then it's 1 plus the rest. And if it's even, then it's just the sum of digits of n over 2. So in other words, I'm rewriting it in the same way as before. S of 2n is S of n. And S of 2n plus 1 is S of n plus 1. So these are the 2 examples which are going to occur throughout the talk. And they look somehow similar, I hope. So they will both be regular sequences. And their asymptotic behavior will be quite different. And that's what I'd like to point out. Okay, so what's the common thing? I start with the sum of digits. I'd like to write that in matrix vector form. So here is the recurrence. And while I consider a vector, v of n is defined to be S of n and a constant sequence in the second component, because constant sequences occur right here. And now I can write v of 2n is, well, by definition, S of 2n. S of 2n is S of n by the recurrence. And I can write that in a very spectacular way as a matrix vector product. Here it is identity matrix times v of n. So that was really exciting, yeah? This matrix vector product. But let's try with odd arguments. If we have v2n plus 1, then by definition s2n plus 1. And now we again use our recurrence, S of n plus 1. And now the matrix vector product is exciting because we have 1, 1, 1, and a 0. So here I actually needed it, yeah? And this shows why I need both components of the vector. Okay, so And as a sneak preview, a regular sequence will be a sequence which is the first component of a vector valued sequence where I can write such recurrences. V2n and V2n plus 1 equals matrix times Vn, matrix times Vn, and the matrix depends on the residue class. I'm switching over to this side, minimum and maximum again. Here are the recurrences. Oh, now I have an m of n and then m of n plus 1 and the constant sequence, which means that my vector is now a three-dimensional vector. And while v of 2n is m of 2n, m of 2n plus 1 and 1, and I can write it in that form using the recurrence. And yeah, here the recurrence and so on and so forth. It works out, and v2n plus 1. Now I have m2n plus 1 in the first component, m of 2n plus 2 in the second component. And here I have, I'm lucky that the recurrence looks as it looks like, so that again, I can write it as a matrix vector product. So as it has the same shape, it is the first component of a vector valued sequence which obeys such a rule. V of 2n, v of 2n plus 1 is a matrix which depends on the residue class times the original vector. And that's a regular sequence. Okay, I should now perhaps define regular sequences. So we had two examples so far. So while we had always q equals 2 so far, q equals 2, so we have a vector valued sequence going to somewhere. And for all residue classes modulo q, I have a matrix which depends on the residue times the original vector v of n. So I have this recurrence relation for all q, for all residues, for all n. And while q is a constant, capital D, this is the dimension of the matrices. So the capital D will not occur frequently in this talk, and at some stage it will suddenly appear and we will all have forgotten what capital D is, the dimension. It doesn't play any role except at one position. Okay, and then these D times D matrices, which must of course be square matrices. Okay, and as I said, the first component of V is a Q regular sequence, has been introduced as a notion in 1992 by Olush and Shellit, and there has been some they have occurred from the asymptotic behavior in many case-by-case examples over the years, and over the last 10 plus years, there has been some kind of systematic approach for the asymptotic analysis. Okay, and this was first formulated in a paper by Dumas in 2013, and then Daniel Krenn and myself did some additional work computing Fourier coefficients and things like that. So what do we know? We have a Q regular sequence. It is the notation as before. And what do we have here? We here have the summatory function of the regular sequence. We have an asymptotic expansion and an error term. So we have an asymptotic expansion of the summatory function. And how does it look like? Okay, so the summatory function up to capital N, we have some polynomial growth, some logarithmic factors. Here we have some suitable periodic functions, phi, and an error term. And some parts are in gray, and I'd like to say that, okay, we have some more details. What is C, for instance? C is the sum of these matrices, of these square matrices, which were in the description of the regular sequence. Sigma of C is the spectrum, so we have to compute eigenvalues of C. Okay, we can do that. And here we have a sum over eigenvalues. Good. So these exponents here will depend on the eigenvalues of C. And then there is this mysterious capital R and this mysterious MC of lambda. The capital R, that's the joint spectral radius of the square matrices. So products of such matrices, norm of it and kth root, and that's the joint spectral radius. And we only take eigenvalues of C into account which are larger than the joint spectral radius because the error term contains the joint spectral radius. We don't have a proof, but we strongly feel that you can't do better in some sense. Yeah, so it's not a limitation of our methods, it's a limitation of the problem. We believe that we have the joint spectral radius here. Okay, and the MC of lambda is the size of the largest Jordan block of C associated with lambda. Okay, so the number of logarithmic terms that's somehow related to the eigenstructure. Okay, a few more words, and then I'll ask the questions I'm going to answer today. These functions are Hölder continuous, the fluctuations, the Fourier series therefore converges, and we can compute Fourier coefficients efficiently. Numerically, we have a functional equation for the Dirichlet series. We have Sage math code. You just enter the joint spectral radius, you enter the matrices, and the rest will be computed. Okay. You are already asking the question I wanted to ask in 2 slides. Okay, so this is one of the basic questions, well, it's not obvious. And I'm going to examine these 2 examples again, say 1 or 2 words, and then come to your question in 2 slides. Because that would really be a pity. Yeah? If we don't have large eigenvalues, then we have a nice lengthy theorem, and all that comes out is a big O term. And that would be really disappointing. And as a spoiler, it can happen. But I don't think it's our fault. I think it's a fault of the sequences we are going to investigate, or we are investigating. Okay, so that was the spoiler for the spoiler. Good. Okay. Here, and the other question is about, do we need to take the summatory function? So here I'm going to draw 2. Well, I should hope that you see something, but no, you don't see a lot. That's a pity. Can I increase that?
Do you see it on the screen there?
No.
What? You could draw it on the whiteboard.
I can't. I'm going to.
You go back over there.
So now I need to increase the size. Oh, okay. If you increase the size too much, then it's going to be worse. Okay, sorry for that. In the picture above, it's the example with min-max. Just plotting the sequence. And you see it has some smooth shape, or at least continuous shape. And in the picture down, you see the sum of digit. And the sum of digit fluctuates. And it does that in an obvious way, because the sum of digit of 15 is large, and the sum of 16 is 1. And you have that pattern all the time. So despite the fact that the recurrences looked quite the same, we have a very different behavior of the sequences. Okay. So now I'm trying to go back to the next slide. I don't dare, because then we don't see. So here, I took the summatory function in both cases. And you see for the sum of digits function, the summatory function is continuous. Well, nothing is really continuous here because it's discrete arguments, but it looks like a continuous function, say. And for the divide and conquer thing, it seems to be smooth, yeah? So, and extremely smooth and perhaps already boring. Which means, and now I might dare to go back to the full screen mode. No. Okay. It seems that for the divide and conquer sequence, it's appropriate to consider the sequence itself. And dividing by n as a normalizing factor, we see something like a fluctuation. Yeah, it's just points and then tending to something more because, well, it's a logarithmic scale. So for the divide and conquer, the function, the sequence itself is good. And for the summatory, for the binary sum of digits, I take the summatory function and get the thing. Okay, so different sequences, different behaviors, and we might be interested in different things. So once we are interested in the sequence itself, because we expect a good shape, and once we are interested in the summatory function, because looking at the sequence itself doesn't give any asymptotic insight. Okay, so and now I might turn back to full screen. Okay. So I already said that, and okay. So questions. So the one question was by Bruno, do we always have enough terms? It was phrased in a different way by Svante when I gave such a talk in Uppsala 1 year ago. He asked, well, if I take the summatory function sufficiently often, will it work then? So it was the more friendly version of your question, because you just asked, does it make as it is? And Svante at least gave me the opportunity of taking the summatory function a finite number of times. So that was the first question. And the second thing is, which was always a recurrent question, so for this divide and conquer sequence, it doesn't make sense to take the summatory function at all. So can we say something? And okay, so these are the questions I'd like to speak about. Okay, spoilers, yes, almost always. So taking this summatory function sufficiently often helps, almost always. And for divide and conquer sequences, I can say something, and I still hope that in a year I can say something else about some other class of sequences, but that project isn't finished yet. So, yeah. Okay. So I should say that all of that, what I'm speaking today, is joint work with Daniel Krenn, whom you know, and Tobias Lechner, whom you probably don't know, who was a master student. Here the result basically is, so sigma of v will be my notation for taking the summatory function. And the result is that if this sum doesn't have an eigenvalue, I assume that C has an eigenvalue which is non-zero. So the only C's which are not covered are those C's where 0 is the only eigenvalue. Okay, I assume there's a non-zero eigenvalue. Then the answer to Svante's question is yes, there is a non-negative integer k, such taking the summatory function k times admits a good asymptotic expansion, as I call it. So there is something before the error term. A small side remark, I don't say anything about the periodic fluctuation. I'm just speaking about the eigenvalues structure. So it might be that the periodic fluctuation vanishes for some weird reason. I can't handle that at the moment. Okay, so, and while there is not much time for a proof, but just to say a few words. If I take the summatory function of a regular sequence is again regular. So I take it. So the summatory function, I can write it as all Qn plus R prime, which are less than that guy. I split it up. This here is either smaller if the n is smaller than capital N, and then I might take everything for R prime, or while I have a few remaining summons for lowercase n equal to capital N. These are the more important terms, and then I have a few more terms over there. And then I use the moving up and inserting the recurrence and doing some magic or non-magic with sums. And here I have the C, and I have that the regular, the summatory function is again has the C here plus something which is small. And so if I do that, I repeat taking the sum of the matrices, which are C, and so now the capital T is back. Remember, it was the dimension. So if I take it k times, then I get dimension power k times C, and this dominates everything, and therefore it works. So that's basically the process. So that's the answer to the first question. And to the second question, Svante, Xianghui, and Tsai looked at divide and conquer sequences of that shape in a series of several papers over the last years. And they could say something about the sequence itself. And whereas we could only say about summatory functions. And so one of their results was if G is small enough, then the sequence itself has a behavior as we have it in our theorem for the summatory function. So, and that somehow intrigued me that they could and we couldn't, yeah? So I wanted to see the connection, and okay, where is the connection? The first thing is, well, I can rewrite that as a regular sequence by doing obvious steps. I don't go into details, at least if the G is regular itself. I can rewrite it, I get matrices and things like that. And now comes, so we are in the same domain, say. And now comes the most important observation. A sequence is the summatory function of its forward difference. Wow. Fundamental theorem of calculus in the discrete version, or whatever you want to call it, which was always my excuse for not considering sequences themselves, because, well, we know that the forward difference of regular sequences is regular. We know that the summatory function of regular sequences is regular. So in principle, I can say, okay, let's take the sequence I have, let's take the forward difference, take the summatory function of the, and so on, and then we are back in business, yeah? And so the question is, what happens in that process with that particular example? And this also gives the answer to Bruno's question earlier. Will there always be a good asymptotic behavior? Well, take the sum of digits, take the forward difference, take the summatory function of that, and you are back. And it's a mess. Good. So can we say something in general? And well, it's some kind of, we set up the forward difference and we do the computation, and then something very weird and nice happens. Namely, the dependence gets simpler. So usually if I take the difference of a regular sequence, I get more terms because I have to take care of everything. And here I don't. Here I have the delta x, which is the forward difference of 2n, is beta times delta x of n plus these toll functions. Yeah, I don't care about the toll function, but the inherent dependency gets easier by taking the forward difference, and therefore all my matrix manipulations become quite simple because the main component is one dimension. And therefore, it's quite simple, and remember that I say it's simple for the next slide, where it's not simple at all, because then we discuss it in 4 cases. And none of these cases is particularly nice. So what are we doing? Well, depending on the sizes of alpha and beta, and depending of the degree of the Toll function, so I'm only considering polynomial Toll functions here, I get different behaviors. Think about master theorems, yeah? And there, if the Toll function is large, the Toll function takes over. If the inherent thing is large, then this one takes over, and then there are some boundary cases, edge cases, where we might have funny things. What do we have here? We have some kind of resonance, yeah, where we have a logarithmic term plus an error term, and all the rest is somehow a mess, where it's just, well, here the question is a lengthy explanation of what the exponent of the logarithmic factor in the error term should be. No details. And that's finally, for the starting example I had earlier on, a plot of the sequence itself and the Fourier series computed with the Fourier coefficients out of that theory. So that's it. Thank you.
Thank you. Questions, comments?
Very simple one. What's the x-axis here?
We are logarithmic scale. So 2 to the, we start with 4, n equals 4, and we end with n equals 1024. Sorry, no labels.
Labels are for losers.
Sorry.
Other questions? Sure. Thank you very much again.